I was looking at Kramer's method of solving systems, and I saw that some systems were solved only using Gauss methods, and some were solved using both Gauss and Kramer's methods. Now, how to differentiate between systems? Now, I want to ask which systems can be solved only using Gauss methods, and which can be solved using both.
So you're asking about solving systems of equations, right? And you are saying that we can use the Gauss method and the Kramer's method, right?
Yes, and I read that some systems can be solved only using Gauss and some can be solved using both. But I want to know which can be solved using only once and which
Which
can be
one do
solved.
you think is more general?
Well, to me, Gauss method looks more general, but
Why? What does the Kramer's method use? So how is the Kramer's method used? We try to identify this is a vector, okay? This is a vector, this is a matrix. And then what the Kramer's method uses, it says that x1, which is only one of the entries in the equation, this is equal to the determinant of updated matrix divided by the determinant of A. Okay, so you remember this schema? So here we insert the answer vector, we put it at x1. Then this is the second column of A and the third column of A. So this is just the columns, okay? This is A1, A2, A3. So it's a ratio of two determinants. And then x3, this would be equal to the ratio of the determinant of these two matrices. And this would be equal to the first column, the second column, and we insert this vector as the third column. And this is divided by A1, A2, and A3. Now, what is the determinant of this matrix B? I'm coming up with a different matrix, which is 1, 2, 0, 1 minus 1, 3. What is the determinant of this matrix? So, can you find the determinant of this matrix B here?
matrix B, it's not a square matrix, so I don't know if it has a determinant though.
That is true. So we cannot find the determinant, which means that the Kramer's method, it is valid only for square matrices. So only for square matrices that are n by n. But the Gauss method, it is n by n. Okay, this is one way that we can say. So which means that the Gauss method is a more general method. So we better use that one when compared to the Kramer's method. Okay.
Okay, thank you, Professor. Now I got it.
You're welcome. Don't worry. So let's assume for a moment that we have a matrix which is, let's say 7, 2, minus 15, minus 4, and we have another matrix which is 5, minus 3, minus 3, 5. So this is a standard basis, and in this standard basis we have posed a problem. Okay? And when we say a problem, often let's assume that we have a linear transformation in the standard basis, and the linear transformations, they are equivalent to matrices. We know how to transform vectors from one basis to another, and how do we do that? We have, let's assume that we have a basis here, which is that this will be basis B1, and we can come up with a matrix PB1, and any vector which is in this basis, we can consider this one, the vector x, as projected in basis B1, then the x itself in the standard basis, this will be transformed as such. We just do P times vector x according to basis B1. Okay, so this is how we transform a single vector. if we are to look at how a linear transformation looks in different bases, then we need to represent a new matrix B in any other basis, which is going to be equal to, let me call this one D, okay? And this will be equal to P inverse times A times P. So this is the way how we can transform a linear transformation. And this linear transformation, it can be described as using the matrix A in the standard basis and matrix D in the new basis. Any two matrices which can be written using such a relationship here, they are called similar matrices. Okay? And similar matrices, they have several common properties, where the most important one is that similar matrices, they have the same eigenvalues. Now, starting from where we left the last time, let's try to identify what could be the best basis for data which is represented by matrix A. Okay? How are we going to find the best basis? Because we know that the standard basis in this case is composed of these two vectors, 1, 0 and 0, 1. And we have to project these into the new basis. And the major objective is to diagonalize these matrices. Okay, that's the best basis. So we can have here, we are dealing with R squared. And R squared, we can come up with an infinite number of different bases, right? But the issue is that we can have only one basis. The A is diagonalized, okay? Diagonalized. So out of an infinite number of possible bases, we should be looking only the one where the matrix A is diagonalized. In order to do this, the diagonalization of a matrix, it happens in the basis where the matrix A does not rotate the vectors x. Okay, so this is what we should go after. This is the eigenvalue equation, and we need to solve the eigenvalue equation, but maybe I can start this here. So let's assume we're going to start with matrix A, and the basis is that we say AX is equal to lambda x, and from here the question is, given A, find lambda, okay, and find vector x. This is what we are going after, and the way to solve this one, we know that the A minus lambda I, where I is the identity matrix, times the vector x, this is a vector, this is equal to another vector. Then then we can have a trivial solution, which is the x, but we want x different from 0. We don't want x to be the trivial solution. And this is possible only for the determinant of A minus lambda I equal to 0. So apparently, this is the initial constraint regarding the values of lambda. So this puts some constraint on this lambda, and then when we write this determinant from here, we come up with an important polynomial, which is going to be Pn in lambda. And this polynomial, this is called the characteristic polynomial. The characteristic polynomial. And let's see what we get. The matrix A, in this case, it is 7, 2, minus 15, minus 4. And then we have to take minus lambda, which is 1, 0, 0, 1. And this would be equal to 7 minus lambda, minus 15, 2, and minus 4 minus lambda, minus 4 minus lambda. So we want the determinant of this matrix to be equal to 0, and the determinant, it would be the product of these two numbers minus these two. Then here we get 7 minus lambda times minus 4 minus lambda plus 30. This is equal to 0. And here we get lambda squared minus 3 lambda, because we have 7 minus 6 lambda plus 4 minus 3 lambda, minus 28 plus 30, this is plus 2. Plus 2, this is equal to 0. At this stage, we will be looking for, so this is our second order polynomial in lambda. This is the characteristic polynomial, and this characteristic polynomial, this is defined by the coefficients of lambda squared, lambda to the power 1, and lambda to the power 0. So the coefficients here, they are 1, minus 3, and 2. Okay? Coefficients of lambda squared, lambda to the power 1, lambda to the power 0, which means that it is the constant value. So this is our characteristic polynomial. Now, with this characteristic polynomial, we should be looking after for two possible solutions. And
Professor, can you repeat again?
Say it again.
Can you repeat the process, like after we say that lambda square minus 3 lambda plus 2 equals to 0?
Yes?
What do we do after that?
We have to solve this polynomial. We have to find the roots of this polynomial. Okay?
But what is pixel of lambda?
Say it again.
Pixel of lambda.
Sinqerisht nuk të kuptoja, më thuajeni?
Tek çfarë kemi shkruar këtu? Është matricë të dyshi?
Jo, this is the polynomial of the order of the second order in lambda with these coefficients. These are the coefficients of lambda squared, lambda to the power 1, and lambda to the power 0. It's just a representation of the coefficients. I'm writing it like a vector. Okay.
Oh, okay. Thank you. Sorry for the interruption.
No, don't worry. It's a good question, but just often I want to clarify that what you are trying to go after is that you need these coefficients. That's the first thing. And for the second order polynomial, you should have 3 coefficients. For a third order polynomial, you should have 4, one more, right? Because you might always have some constant values. You don't always have lambda to the power n, lambda to the power n minus 1, and lambda to the power 1. You also have lambda to the power 0, so don't forget this. And but your intervention was a good one. Now we need to find what are the roots of this polynomial.
Professor, sorry to interrupt. Can you just make a quick recap of what basically what you're doing here? Because I joined a little late. We had a quiz, so why are these calculations happening? What's the goal here?
Yes, and the fact që se vjen dikush tjetër më vonë pas 10 minutash, ndoshta detyrohem të përsëris gjitha nga fillimi. Si e tutje. Let's say it again. So what we are doing here is that, as a very short recap in 2 sentences, is that we have a standard basis where we have 2 linear transformations, because we know one linear transformation which is represented by the matrix A, and another linear transformation which is represented by matrix B. Now we want to identify the best basis where matrix A and B are diagonalized. Now, if this is the standard basis, this is SB standard basis because it's composed of 1, 0, 0, 1. And this is R squared. It is R squared because this is the basis for the R squared. I think there is no question about that. And R squared has an infinite number of different bases. Okay? So we cannot constrain it. We can always come up with some other rotations of the axis. But only in one basis, A is diagonalized. Okay? This is what we are going after. And the basis which diagonalizes a matrix A is one which is composed of the eigenvectors. So at this stage, we are trying to go after the eigenvectors. So here, in this case, we can say that we have we can reformulate this statement, which is will be the following. Given a matrix A, okay, we have to find eigenvalues, and we need to find also the eigenvectors. So this is our task. Always we will be given a matrix, and we have to go after to find eigenvalues and the eigenvectors. Now, if a matrix A, it is described as n by n, and by the way, we can do this only if A is this. What do you understand from this?
If A is a square matrix.
It's a square matrix, that is true. So we can never diagonalize a matrix, which is, we can never diagonalize a matrix which is not a square. So in this case, traditionally, we might expect that from an n by n matrix, we expect to get a characteristic polynomial of order n in lambda, where lambda is the eigenvalue. We try to find the lambda and a polynomial of order n. How many roots does the polynomial have?
It depends on the degree.
Well, if it is order n, we expect n roots, right?
Yes.
Okay, so if it is a polynomial of the 8th order, how many roots are we after? Do we need to find?
8.
8, that's correct. So if you have a polynomial that looks like this, x to the power 8 is equal to 1. Can you tell me the roots?
Is that equal to 1, Professor? Because I can't see it.
That is 1. X to the power 8 is equal to 1. So can you tell me 8 roots?
It's plus and minus 1, but there's 4 sets of plus and minus 1.
What else? We have 6 more to go.
Well, I think it's those values that you wrote, but they're repeated.
Professor, what about the imaginary numbers?
What about what?
Imaginary numbers.
If there are numbers?
Imaginary.
Imaginary numbers, yes, we have to include those. So give me some imaginary numbers that satisfy this condition.
The only imaginary numbers are, I guess, or not.
So I can give this I.
Yes, I.
Minus I. That is 4. Where we need 4
I
more.
squared.
What is that?
I squared. I to the power of 2.
But I squared is minus 1. It's already here. So we need 4 more values that we need to determine those. So we should remember that the square root of minus 1 is equal to I, which means that I squared would be minus 1, and I to the power 4 is equal to 1, and I to the power 8 is 1. So this does satisfy. Okay, we know that, but we should be looking for 4 more values, and we will find that later. Okay, we'll cover that issue later. Let's come back here. So we should be looking at a polynomial of nth order, we need n roots, n solutions, which means that if we have a polynomial of 16th degree, we should get 16 different roots, okay? But the issue is that the real domain is very limited, so sometimes not all the roots are in the real number space, okay? So if you see here, in the real number space, we have only 1 plus 1 minus 1. We have only 2. 6 more roots should be in the complex number domain, or in the complex number space. So we are moving this way. We come back to our original problem. We have a polynomial to solve, and this can be described as lambda minus 1 times lambda minus 2. This is equal to 0. So at this stage, we see that lambda 1 is equal to 1, okay, and lambda 2 is equal to 2. So these are 2 roots, and if we are to draw this polynomial, the graph is going to look something like this. So we know that here we have 1 root which is 1 root which is 2. So we expect the graph of y is equal to lambda squared minus 3 lambda plus 2. And the intersection here will provide the two roots that we just found. Now, for each lambda that we find, we have to identify also the eigenvector. So then we start doing this step by step, and we have the following. For lambda 1 equal to 1. What is the equation that we have to deal with? The equation that we have to solve is the following. Is that we have A minus lambda I times a vector which is 2 by 1, such as AB. This should be equal to what? 0, 0. Okay? So A minus lambda I is equal to, what is A minus lambda I? The A, it's here. So it's 7 minus 1, this is going to be 6 minus 15, 2 minus 5, okay, this is A minus lambda I, and multiplied by AB, this is equal to 0, 0. So what is A and B? So what is the fundamental
The
equation?
null space of that matrix.
Yes, it is, the null space. So how many unknowns do we have here?
2 unknowns.
How many equations do we need?
2.
Can we get 2 equations from here?
Professor, sorry.
Yes.
How did you obtain the matrix A minus lambda I? Did you subtract the values or?
Yes, lambda is 1. So this is the matrix A, and subtracted 1 from the diagonal terms.
Why only the diagonal terms?
Because this is minus lambda I, this is the identity matrix.
Oh, okay, so you multiply lambda with the identity matrix, then you subtract.
Yeah, so it is in principle this equation here, this expression here.
Okay.
Okay? So, or we could have written it in this way. So allow me to, we can also do it like this. So we can assume that this A, so let's remember the equation. The equation was this. AX is equal to lambda x, right? A, it is 7, 2, minus 15, minus 4, times the unknown vector AB. This is equal to 1 times AB, right? Would you agree, Joe?
Yes.
So this is 1 times A and 1 times B. So then, what equation can we find? So, but this is equivalent to this. Would you agree with that, Joe? These two statements?
Yes, it seems equivalent.
Yeah. Okay, thanks. So tell me, what equation can we come up from here?
You get 7a minus 15b
Is equal to what?
equals a,
Yes, what is the other equation?
and 2a minus 4b equals b.
And here we get the same, right? Here we get 6a minus 15b. This is 0. And 2a minus 5b is also 0, right? Would you agree that we have the same statement here? So this pair of equations is the same as this pair of equations. Would you agree?
Yes.
Yes. Okay. So the next question is, let's find, and do you see any similarity between the first equation and the second?
They're the same.
They are the same. So we have 2 unknowns. For 2 unknowns, we need 2 equations. And we don't really have 2 equations because we see that the first equation and the second are the same, which is fine. And we expect this because these 2 equations have to be the same because the determinant is equal to 0 when lambda is 1. So when lambda is 1, it was a constraint that we put it. We wanted this. If you see this expression here, we said determinant minus lambda I is 0. So then, in the end, we end up with an expression which is 2a is equal to 5b. So what is the pair of numbers a and b which satisfy this condition? So 5, 2 is a good option. Would you agree with this? So for lambda 1 equal to 1, the corresponding eigenvector, it is equal to 5, 2. Then let's look for the other eigenvalue. So which is the following. So let's say for lambda 2 equal to 2, we get the following expression. We have here, so let's write this again. 7 minus 2, this is 5, minus 15. We get here 2, and minus 6. So times AB, this has to be 0, 0. For this expression, we again get the similar. Is this correct? I think this is true. If we multiply by 5 over 2, yes. So the only equation we get here is 2a minus 6b, this is 0. Okay, yeah, so we get 2a, it's equal to 6b, a is equal to 3b. Then the pair of numbers a and b which satisfy this condition, it's equal to what would you say? So if lambda 2 is equal to 2, the eigenvector here, it has to be a pair of numbers which is 3, 1. Okay, so here we have the other eigenvector. So it looks like for the linear transformation, which is represented by the matrix A, which is 7, 2 minus 15 minus 4, the basis which is going to diagonalize the matrix A is composed of these two vectors, 5, 2 and 3, 1. So here we have this 5, 2 and 3, 1. So this constitutes also the matrix which diagonalizes the matrix A. And the question is that how is A projected here? A, if you remember from the last session, the matrix A, when we project it in the new basis composed of these two vectors, is going to be a diagonal matrix with the diagonals as 1 and 2. Okay, so this is what we're going to get for this new basis. Now let's try to solve the same problem using the other matrix, which is 5 minus 3 minus 3, 5. Now, if we try to do this, let's try to see what we obtain. We have here 5.
Professor, I have a question.
Yes.
When you found the eigenvectors,
Yes.
I think we can find infinitely many values for A and B.
Yes, that is true.
So how do you? I mean, is any value okay, or do you just?
Any value is fine. Any value is good. No, there's no problem with that. Okay.
You just choose one arbitrarily. So.
That is correct. So a good choice. So let's say that the matrix P, or let me just write let me think for a moment. Yeah. So assume that we have here 5, 2. This vector 5, 2 is an eigenvector, and I can put it here. It's fine. But this one is also possible. Minus 5, minus 2. Or 10 and 4. We can multiply them like this. But the best one is one where the vector is normalized. How can we normalize this vector? This means that we want to express that vector, what's the name? having a length 1. How can we normalize this one? What is the magnitude of this vector? 5, 2. So what is the magnitude of this vector, which is 5, 2? What is the length of the vector?
The square root of 29.
All right. Square root of what?
Square root of 29.
29. You are right. So this is 1, 2. So this is 5. This is 2. And the length here is the square root of 29. So the best solution should be the following. 1 over the square root of 29 times 5, 2. Okay? This would be the best bet. And then, regarding the other eigenvector, we have here the vector 3, 1. So this is an eigenvector, but this is also a possible one, minus 3 minus 1. Or multiplied by 10, 30 and 10. They are all equivalent. But the best one would be one that, what is the magnitude or the norm of this vector?
Root of 10.
Root of 10.
Root of 10. So here we have 1 over the square root of 10 multiplied by 3 and 1. Okay, so this could be the best choices.
So they are unit vectors in that case, unit eigenvectors.
Yeah, they are unit length vectors, yes. But it is easy for us to look at integer numbers, so because this would be an irrational number, an irrational number, it has an infinite, we cannot describe them with infinite precision. This is a key word I often use it, because I know that it will become useful to you in the future, because the square root of 29 is irrational. You cannot write it down with infinite precision, because you need an infinite number of numbers after the comma. So I'm going to erase this one. This was clear to you.
Can I ask you something too?
Yes.
The matrix composed of eigenvectors, what is it called? Is it a transformational matrix?
Well, you can call it transition matrix. Okay, I don't know. It's a matrix which diagonalizes the matrix A. Okay.
So we go from the matrix A in the standard basis with that matrix to the matrix D in B1 base.
Yes, and actually I have written it here, but so what we need to, the way that the matrix A is transformed is in this way. It was written here, but I just erased it. So this is going to be times P. So it was a good question. Now let me take out some of the. So let me take away this one. At least we have the solution of this one for one case. And let's help me here. So P, we know what P was, right? P is 5, 2, 5, 2, 3, 1. What is P inverse? What is P inverse?
Minus 1.
We exchange 1 and 5. This is minus 3, minus 2. Okay. What is the determinant of P?
Minus 1.
So 1 divided by minus 1, because for any matrix which is A, B, C, D, the inverse, it is written as, so if you have any matrix A, B, C, D, the inverse, it is defined as 1 divided by the determinant times dA minus B minus C. So now we know the P inverse, then the P inverse, this is equal to, let's insert the minus sign inside, this is minus 1, 3, 2, minus 5, okay? So then, let's see what we obtain here. This is equal to what is this? Minus 1 minus 5, this is minus 1, minus 5, 3 and 2. Let's multiply this with matrix A, which is 7, 2, minus 15, minus 4, and let's multiply by the matrix P, which is 5, 2, 3, 1. We know what standard basis looks like, let me take this away, and this is equal to, so what is the multiplication of these two matrices? We get 7 times 5, it is 35 minus 30, this is 5. Then we have 7 times 3, we get 21, minus 15, we get 6, then 2 times 5, 10 minus 8, this is 2, then 2 times 3, 6 minus 4, this is 2. Okay, then let's multiply here. This is minus 1, 3, 2, minus 5. This is equal to minus 5 plus 6, 1, minus 6 plus 6, 0, 10 minus 10, 0, 2 times 6, it is 12, minus 10, this is 2, okay? So this is how we diagonalize this matrix A, and this is what we obtain here. So this matrix P that you asked me is a Mora. It is the matrix which correctly diagonalizes the matrix A. Okay?
Okay, now it's clear.
So it's here, you're welcome. And then what we can add here, let's bring up the old techniques so that we don't forget those. Assume that, let's say that we're given that the vector x in the basis b is equal to 2 minus 3. The question is, what is x? How can we find x? Who can help me here?
We have to multiply the P matrix with X.
That's correct. Okay, so let's not forget that. How do we transform vectors? This is how we do them. How do we transform matrices? The matrices, but we do it like this. P inverse P, this is equal to D. Okay? Or we can also say that A is equal to P times D times P inverse. So we should be able to see this. So it looks like if we are, because let me see it. So if we are in the new basis, a vector x is multiplied by p. If we are again in the new basis, we multiply by p, but we have to include also this one in the end. Okay. Yeah. Is it clear? So the diagonalization, this is how it is done. We see this example here, and again, let's finish this one. What is x? If this is the xp, this is going to be the 5, 2, 3, 1, 5, 2, 3, 1. Multiply the vector 2 minus 3, and this will be equal to 5, 10 minus 9, 1, and 4 minus 3, 1. Really? We've got the vector 1, 1. So let's add this into this picture, and let's just also as a reminder. So apparently, a vector which is 2 minus 3 in this domain, this is going to be equal to a vector which is 1, 1. Okay. And this is the standard basis. This is the new basis. Okay. And this new basis is composed of these two eigenvectors of the matrix A. Are we good here? Then let's solve for the other matrix B. For the matrix B, we have done this matrix before. So if you remember, we did this one the last week. But as a reminder, let's try to follow the procedure as we always used to do it. So we have here 5 minus 3, 5. We subtract minus lambda I. So this is what identity matrix is, right? So this is equal. So in any assignment, the first thing that I should see in your exam papers is this 5 minus lambda minus 3 minus 3. We have again 5 minus lambda. Okay, and here the determinant of this 2 by 2 matrix should be equal to 0. So the product of these minus these two should equal to 0. Then we're going to get a polynomial of second order in lambda. This is 5 minus lambda squared minus 9. This is 0. And here we obtain the lambda squared minus 10 lambda plus 25 minus 9. This is 0. So here we get the lambda squared minus 10 lambda plus 16, this is 0. these lambdas, they multiply each other, lambda times lambda, and 16, it is minus 8 minus 2, right? So if we multiply minus 8 minus 2, we get 16. But then here we have the option that minus 8 lambda minus 2 lambda, we get this. So this looks like a good factorization. So we can write this one as lambda minus 2 times lambda minus 8, this is 0. Then lambda 1 is equal to 2, and lambda 2 is equal to 8. So we found eigenvalues. If we found eigenvalues, we can immediately say that the new basis, let me use the board like this, the new basis, it will diagonalize the matrix A, and we will get the following, 2, 8. Okay? We can confirm this later, okay? I know that we can confirm this later, but it looks like, sorry, we are diagonalizing matrix B. So B will look like 2008 in the new domain. Okay? What we don't know yet is, which we have not identified for the moment, is that we need to identify also the eigenvectors, or the basis of this new domain. Okay? So if you look at the big picture, this is the standard basis, this is the basis which can diagonalize the A, and now we are trying to determine what is this new basis here. What does it mean to find the new domain completely? Is to find the eigenvectors. So,
Professor, sorry to interrupt. Can you find matrix D always like this? Like you just write the roots as diagonal terms? And
yes, that's true.
Okay.
Professor, may I say something? Because I was late, I arrived here last week, I missed it. What is diagonalization in theorem?
What is diagonalization in what?
In theorem, how do we understand diagonalization?
Diagonalization, it is trying to project your data set into a better axis. So using the Cartesian coordinate axis, which is x and y, as you can see it here, this is not always the best basis, okay? It's not always good to use this one. What can happen is that you might rotate your domain, and maybe your problem, it gets simpler, okay? Or these two vectors, you can rotate them some angle, but then they don't even have to be at 90 degrees. You can get a pair of vectors which are going to represent, where if you project your problem in this basis, it will look simpler. Is it clear?
Yes, and the result will be always like 1, 0, and 0 something. For example, leading coefficients.
Say it again.
And the result of this D that we found here will be like 1, 0, 0, 2, and so on.
I'm missing some part of it, what you're saying. Maybe it's because the speakers are not good. So you're saying that, mund ta përsërish dhe një shqip?
Profesor, do të thënë zgjidhja siç e kemi gjetë kjo është 1002. Do të thënë kështu deri gjithmonë zgjidhja. Kjo është, do të thënë, ajo që ka gjetur nga diagonalization, që ta thjeshtojmë matriksin, apo?
So the matrix, the linear transformation, it is more elegant if you see it like this, okay? Because the thing is that initially, if we have a problem like this, it looks like we have coupling of two coordinate systems. So if you have here minus 15 and 2, you can interpret this one as if two axes are interfering with each other. So the projection of one axis onto the other is minus 15. But here, you have removed, so you have decoupled the system. You are electronics engineering, and for you, coupling and decoupling is very important. So now, being able to decouple them, that means that you describe one variable, not as a function of the other variables. Okay, you describe how one variable changes only as a function of itself. Okay. So we will offer examples. Maybe a very good example is the following. Let's assume for a moment we have let's say this one. We have a derivative of x with respect to time. This is equal to let's read it from there. This is equal to 7x minus 15y. Okay, we will come to this problem after one session. Okay. Can you read the red color? Is it clear?
Yes, it is clear.
And we can have also the derivative of y with respect to time is equal to what? 2x minus 4y. Now, this is a coupled system. So this system, it is coupled. Why? Because x is a function of x and y. Okay, we don't like it. It's hard to solve this system. Okay, what about y? Y depends both in x and y. So what is the solution? The solution is to rotate this coordinate system in some way so that we can solve this one in an easier way. What could it be? And by the way, what is this? This is a system of equation. So far, we have solved systems of linear equations which look like this: 3x plus 4y, this is equal to 5, minus x plus y, this is equal to 6. We've been solving this a lot, right? Now we need to solve this. But the problem is that, and how do we represent this one? This one, we represent it like this. The derivative of x with respect to time, and this is the derivative of y with respect to time. These are derivatives which you have done them in calculus, and you are specialists of how the differentiation works. This matrix, which is 2 by 1, okay, is equal to 7 minus 15 times 2 times minus 4. I want you to be very attentive, please, because this is very important. So, would you agree that this system of equation is the same as this one here? Yes, right? Because this is a 2 by 2 matrix. You multiply with 2 by 1, we get this. So, this is the system of equation. This is the matrix representation form. And now, the question is, can we diagonalize this? And we say, yes, we took linear algebra. And we know how to diagonalize this one. And what we can do is the following. We can express this in a new coordinate system, dx over d time, and dy, so derivative of y with respect to time, and this is equal to, what is the diagonalization matrix? Can you tell this to me? How did we diagonalize this one? Who can answer this from the class?
So I get to use the formula, respective formula.
Say it again.
Been formula مثلا تدرس.
Have a look at the board. It's written on the board. What is this matrix?
Мне professor Spandek.
5, 2, 3, 1.
No.
Is it 1002?
Exactly. Yes, this is 0, 2.
Oh, okay. So it's a diagonalized matrix. No
We
transformation.
diagonalize it, okay? And this is as a function of capital X, and here we have capital Y, okay? Now, your question, and can you tell me your name because I don't recognize voices yet?
Albino بس.
Albino. Okay, faleminderit Albino që ma shumë konfirmove. Pra, let's not forget, your question is a good one. You're asking this one a little too early, but since you have your interest, we'll go over it, okay? We're going to discuss this. So why do we need to do this? Why do we do the diagonalization? We do this because we can, this system is coupled, right? Why? Janë të qetësuar, që do thotë janë të varë, të ndërzuara shumë keq njëra tjetrën. And what we can do is that if you see this problem here, we change the coordinate system, and now this system is called decoupled. And solving a decoupled system of equations is much easier. So what is the first equation here now? Now that we decouple this. And again, let's have a look. This is the diagonal terms, this is the diagonal terms, and is x coupled with y? What can you say here, Albino? Albino.
Yes, professor. So,
Is this capital X, is it coupled with y? It is not coupled because this is what you see. Sa del kjo? Po shkruaj ekvacionin këtu tek matrica re. Sa del kjo? Do të ishte të të para x. Je dakord?
Po, ndërsa e dyta del 2 përmbitator paras me 2y.
Exact. Pra, derivati i y-it madh është i barabartë me 2y. Nuk është me y i vogël. Kush të përqendri më shumë Albino? Which one does it look simpler? This system or this system?
The second one. But I need to understand the way how to get to the second one, you know what I mean? I don't want to learn it by heart, I want to learn it by logic. And I'm trying to...
Well, the logic is this, that if you're given a system of differential equations when you go to the second year numerical analysis course, whoever is going to teach to you, they're going to ask you to solve this. They'll say, okay, I can solve this one using linear algebra because linear algebra simplifies them a lot. So you say that you want to know the logic. The logic is this. This system of differential equations, it's here. You have a matrix here. You can diagonalize it. It will simplify it. You diagonalize it like this. How do you do it? You get this matrix A, you find the eigenvectors, right? And where are the eigenvectors? There are these two terms here, okay? And then, what is a diagonal matrix? Here you have it. You put the eigenvalues, okay? And then, Albino, what is the solution here? You have dx with respect to dt is equal to x. What is the solution here? How can you solve this?
You can integrate.
Sorry?
Integration, maybe?
Nuk dëgjoj.
Integrimi, professor?
Po, integrim të dy krahat, ke të drejtë. Por mirë është i ndajë këto variante. Let's try to solve this one like this. You know derivatives, and you know you need to solve this one. So what you can do is you can multiply both sides of the equation with 1 over x, okay? So we multiply also here with 1 over x. Then, what do you get? You get 1 over capital X dx over dt. This is equal to 1, right? What can you do next? We can multiply with delta t, both sides of the equation. We multiply here delta t and here delta t. So what you get the dx over x. This is equal to dt. Okay? Then the next step is the following. You can integrate both sides. What is the integral of 1 over x?
X to the power of minus 1? No.
It's natural logarithm of x. Did you forget this so fast?
Ngatrova me...
But we are good, right? So it's ln of x. Would you agree?
Yes.
So then what you can do is you can take the exponential of both sides. So you can do the following. Exponential of ln of x. This is equal to exponential of t. You can still see this. Exponential and natural logarithm, they are inverse functions. So you can get here that x is equal to e to the power t. Okay? So we solve this one. Now, what is the solution for y? The solution for y is going to be this e to the power 2t. So you see, we solve this problem. Now that we know x and y, we know how to transform a vector from one domain to the other. And you see why this became so useful? So we can easily determine what was x and y. Then we can find, now that we know x and y, what is this x and y? X and y, this is the pair of vectors, how they look here. Okay? Now, what remains for us is to find this little x and little y in the standard basis. How will we do that? In order to find the little x and y, this would be equal to, x and y is equal to, so the predominant, CJ Dixon, how can you find this?
The transformation matrix 5231.
Exactly.
E to the power of t.
Yes. that's wrong, but not wrong, but we can substitute what we know, e to the power t and e to the power 2t. Okay? So then what is x and y? Let's try to solve this here. Let's write this down. Let's not miss the previous result. We get 1, 1. And here, the x and y, for the differential equation, it is 5e to the power t, 5e to the power t, and then plus 3e to the power 2t, plus 3e to the power 2t. This is x, y is equal to 2e to the power t, plus e to the power 2t. Okay? So you see, using linear algebra, you were very good at, given this differential equation, you diagonalize the problem, you got this, and with minimal information of calculus, so you did not need to be specialist in calculus, you identified that this differential equation, after you transformed it and came back, you found that the roots that satisfy this condition is 5e to the power t plus 3e to the power 2t and 2et plus 2e to the power 2t. Now, you write this down, and as your homework, what you can do is that you substitute these values here and confirm that we have the correct answer. Okay? So this is your homework. Check this one and make sure that we solved this one correctly. Albino, is it a little more clear?
Yes, Professor, a bit more clear, but I have one last question. Why did we choose 1, 0, 0, 2 and not other vector in our solution? There, the bottom one, we said decoupled.
Why did we use this one?
Yes.
We solved this one because this is the only possibility to diagonalize A. So if you start with matrix A, I mean, did you start with this?
Yes.
Yes, which means that we started with this. And now there is only one way to diagonalize A. Because A has only two distinct eigenvalues. So why did we choose this one? Because this is the only way, this is the only corresponding diagonal matrix which corresponds to A. That's it.
So, yeah, so we did the formula and then we used to find the values of x and y.
Yes, yes, exactly. But what is essential is, if you start with A, this is the only possible diagonalization matrix. Okay?
I understand. Thank you.
You're welcome. So, and now, okay, we solved A, fine. Now, let's go to another matrix. Let's pick up this 5 minus 3 minus 3, 5. How would it look like? I mean, again, we found out that it has two eigenvalues, 2 and 8. So if you are going to diagonalize the B will be projected in this basis. Albino, ce nu chimice bază străină? Ce nu chimice de acolo?
Sai?
What do we need to find for this new domain?
Maybe x and y correspond to B?
Oh, okay, we have no eigenvector. We haven't found eigenvectors yet. Now, this is a beautiful board. I don't know what should I erase, but let me erase this one. So for lambda 1 equal to 2. So for lambda 1 equal to 2. What do we get? For lambda 1 is equal to 2. Let's write it the simplest way, or the like this. This is 5 minus 3, 5 times AB. This is equal to what? This is equal to 2AB, right? 2AB. So this is AX is equal to lambda x. So what is A and B here? What is the first equation? The first equation is 5A minus 3B is equal to 2. Okay? So what do we get from the first expression? We get 3A is equal to 3B. Is equal to 3B. So what is a pair of vectors A and B which satisfy this condition? What is A and B?
1 and 1.
1 and 1, that's good.
Professor, you're not even doing the second equation. Maybe that's not necessary, right?
The second one is useless. Let's check that. The second equation is minus 3a plus 5b is equal to 2b. So what is this? If you notice, this is the second equation, right?
Yeah, it's the same. So
minus 3a is equal to minus 3b, so it's useless. Now,
so do you always get like these redundant equations with these matrices?
of course, always, because subset determinant is 0. When is the determinant is equal to 0? Determinant is equal to 0 whenever we have a useless equation, whenever we have a redundant equation. Okay, so if we have a matrix which is 3 by 3, 1 will always be 0, which means that one of the rows will be 0, which means that we can get a rank 2 matrix out of the 3 by 3 matrix, right? This is a 2 by 2 matrix, the rank is 1, that means that we have only one equation, which means that we have one free variable, which means that the dimension of the null space for a specific lambda is equal to 1. Okay? So this is 1, 1. And now we can also write this one like this, 1 over the square root of 2, 1, 1. And this is not equal, but this is equivalent. So we can put 3 lines. They're not equal. For sure, they're not equal. But we're looking for the basis. So here we have 1, 1. 1, 1. And what is the other eigenvector? 4 for lambda 2 equal to 8. We get 5 minus 3, 5 times AB. This is equal to 8AB. So what is a single equation that we can get from here? Let me pick someone from the class, but I need a fast answer. So I pick Reda. If not Reda, we have Cindy. Okay, well, let me do this. So we get here 5a minus 3b. This is equal to 8a. So what is the relationship we get from here? This is, we get the 5a to the other side, so we have minus 3b is equal to 3a. So what is the relationship between a and b? They are negative of each other, so we get here 1 minus 1. Okay, so it looks like in order, and again, let's delete this one, and let's see how the matrix B is diagonalized. Now, this is matrix P. It is 1, 1 minus 1. So 1, 1, 1 minus 1. So what is the inverse of this? Let me write for a moment. This P is equal to 1, 1, 1 minus 1. What is the determinant here? Determinant is minus 2. So here, determinant is equal to minus 2. That means that P inverse is equal to 1 divided by minus 2 times, we interchange the numbers here, this becomes minus 1, 1, and this is minus 1, minus 1. So P inverse is equal to 1 over 2. Let's put the minus sign inside. This is 1, 1, 1, minus 1. So we found the P inverse. Then let's consider this all the diagonal matrix for A, dA. And here, the dB, this will be equal to P inverse times B times P. And P inverse, it is 1, 1, 1 minus 1. It's 1 over 2 here. Okay, so this is 1 over 2. I forgot to write that. Then this is 5 minus 3, 5 minus 3, minus 3, 5 times the matrix P. Sorry, the matrix P, it is 1, 1, 1, minus 1. Okay, so this was P and P inverse. If we look, we saw how we got those. So if we multiply these, we get the following 2 by 2 matrix, which is 5 minus 3, this is 2. Then we get 5 plus 3, this is 8. Then we get minus 2. And here we get minus 3 minus 5 minus 8. Minus 8. Multiplied by 1 over 2, 1, 1, 1 minus 1, and this is equal to 1 over 2. This is 2. What is this? This is 2 minus 2. We get 0. So we made a mistake somewhere, apparently. Oh, okay. Wait, this is 1 over 2. Where did we make a mistake here? I don't see it. Why don't I see it? Zero. I don't see where the mistake is. 5, 2, 8. Do you see where? Again, we get here 1 minus 1. 1 minus 1. Inverse here. This is 1. 1, 1, 1. I don't see this for a moment. Do you see where the mistake is?
I feel that the matrix 2, 8 minus 2 minus 8, the minus 2 must be 2. I don't know. I'm not sure, but I think it's 2.
Where is 2?
At the last matrix.
Where? It means over here?
No, minus 2. Inside the matrix.
Here?
No, the other minus 2 should be 2, I think.
No, this is... Oh, you are right. This is 2. That's correct, because here 3 times 1, that's 3. Sorry, minus 3 plus 5, this is plus 2. Okay, this is plus 2. So this was the mistake then. Then if this is the case, here we get 4. Then we get the 1, 1, this is 0. This is 0. And then we get the 16. Okay, 16, that's true. So if we divide this by 1 over 2, this is 2, 0, 0, 8. Okay. Okay, so it looks like we got this diagonal matrix which we obtained initially. So as a result, what we see here, we see that we have the standard basis. We gave two linear transformations which are represented by matrix A and B. We diagonalized A, and it looks like when it is diagonalized, this is how it is going to look like 1, 2, 0, 0. And then, but to diagonalize A, we use this basis. Then, when it comes to the matrix B, which is this, the only diagonal version of this matrix B here is this one. Okay, and this is done using these eigenvectors, which are shown here. And we checked again, and we made sure that really the diagonalized version of A, this is how it's going to be. And we did also an extra example here.
Profesor?
Yes.
Një pyetje.
Oh.
Ne kemi formulën e D-s për domethënë për ta vërtetuar që është ashtu 2008. Pra mund ta shkruajmë neve direkt të shkurt, domethënë kur kemi Eigenvalues. A mund ta bëjmë direkt 2008 për formulën?
Po, mund ta përdorim, po.
Okay.
So you can use the eigenvalues because always the diagonalized version of any square matrix, it includes in the diagonal terms the eigenvalues. You just place them there, you are good to go. Okay. Okay. Any other question?
Professor, how do we know which one to put in the first row and which eigenvalue to put in the second row?
This is a good question, and regarding that, we can write the following. So, allow me to take this out because this was just workout exercises. So, this one, you can do it, let me write it like this as a board. So, here we have, you said that how do we know which one to write first? So, if you write a P like this, we have 5, 2. Actually, we need to know also the inverse. What is the inverse? Yeah. So, or let me say it like this immediately. If you write 1, 2, this would be your P. Okay. But if you write a D21, so this is 3152. If you use this as a P, then the D diagonal matrix will be equal to 2001. So you switch these two, and you should switch also these two columns, okay?
Okay, but do we still do diagonalization? So it is still called diagonalization.
Of course it does, don't worry. You can check this one. You can check and you'll find out that if you, so this is a good question, if you have a 3 by 3 matrix and you keep switching because you have a few permutations, the first and the third, or the second with the first, what happens is that you change the places here, but then you have also to reorder all the eigenvectors, whether it's the first column, the second column, or the third column. Okay? Now, let's see another example. So we did the diagonalization. We did a good exercise because it was, you also asked very good questions. You interrupted me enough. But then, let's see, we have the geometrical representation. If you want, we can have a short break. Let's stop this one and start again.